Next, we have Xinyu Zhang from DESI, who will tell us about hidden symmetry in 4D n equals to superconformal field theories. Please.
Okay, thanks for the introduction, and thank you for giving me this opportunity to speak here. The title of my talk is Hidden Symmetry in 4D n 2 superconformal field theories. This is based on my work in progress with Enrico, Hanno, Ali, and Curtis. Hopefully, the paper will come out soon. Symmetries play an important role in modern theoretical physics. We learn from the standard textbooks that Lie groups and Lie algebras provide the natural framework to describe continuous symmetries. However, it has been known for a long time that not all continuous symmetries can be described in the notion of Lie groups and Lie algebras. A more flexible and powerful treatment is based on quasi-Hopf algebras. Recently, it was found that there's a large class of angle 2 superconformal field theories that are integrable in the planar limit in the same sense as the planar integrability of angle 4 super-Yang-Mills theory. And in this study, a quantum group of PSU22/4 with a deformation kappa that I will define later shows up in the one-loop spectral problem. Inspired by this work, we would like to have a better understanding of the quantum symmetry underlying the angle 2 superconformal field theories. Today, we will focus on a simple example of angle 2 superconformal field theory, which is the quiver gauge theory, whose quiver diagram is the thinking diagram of A1 hat. This theory can be obtained from the 4D angle 4 super-Yang-Mills theory by first doing a Z2 orbifold projection, and then performing a exactly marginal deformation. And here is the quiver diagram. We have two gauge groups, SUN1 and SUN2. And from the angle 4 super-Yang-Mills theory, we have three complex scalars, X, Y, Z. And after the Z2 orbifold, X decomposed into Q12 and Q21, Y into Q2.12 and Q2.21. They are in the bifundamental representation of the gauge group. And Z decomposed into phi1 and phi2, and they transform in the adjoint representation. The superpotential of this quiver theory takes this form, and here G1 and G2 are the gauge couplings of two gauge groups. In string theory, this theory is realized as the water volume theory of n coincident D3 brings, probing the A1 type ALE space, which is the blow up of Z2 mod Z2. We also need to turn on a background B field. As everyone knows, in angle 4 super-Yang-Mills theory, the superpotential is manifestly invariant on the SU3 symmetry, which transforms X, Y, and Z. And this SU3 is a subgroup of the SU4 asymmetry. Naively, in our angle 2 theory, the superpotential is only invariant on the SU2 times U1 subgroup of this SU3. Here, SU2 rotates X and Y, and the U1 is a scaling of X, Y, Z. The other generators, which transform between X and Z and Y and Z, are broken. Because of this broken from this SU3 down to SU2 times U1, we can use the commutation relation of the superconformal algebra to show that the superconformal symmetry is broken from PSU22/4 down to SU22/2. In the following, we will focus on the XZ sector. In this sector, we have a SU2 group with the generator E, F, and H. We can assign their transformation rules in this way. E acting on Q and transfer it to phi, F acting on phi and transfer it to Q, and H rescales phi and Q. It's easy to check that E, F, and H satisfy the standard commutation relation of SU2. Naively, we will see that only the U1 subgroup of this SU2 preserve the superpotential. If we act E or F on this superpotential, we simply get non-zero result. So how to fix this? the way out is to deform the universal enveloping algebra of this SU2 Lie algebra by modifying the action on the n particle states. As we showed before, this only defines the action on single particle states. So in the conventional case, here we take 3 particle states as an example. We use the Leibniz rule. The generator acting on 3 particle states is simply the sum of 3 terms, and each term is act on 1 particle state and leave the other 2 particles invariant. However, if we allow a quasi-Hopf type symmetry, we can introduce a non-trivial action on multi-particle states. And this is described by a non-trivial coproduct. We keep the action of H invariant because it's already invariant. But for the E and F, we introduce the non-trivial action of K. And we can show that if we take the we take the following action of K, which acts on Q2 and phi in this way, the E and F acting on the superpotential equal to 0. Here we see that this kappa is the ratio of 2 gauge couplings. And if the couplings are equal to 0, then kappa equal to 1. And the action of Ke and Kf are the same. But if they are different, we have different assignment of kappa. This means that we have a quantum enveloping algebra of SU2 with a deformation parameter kappa, and this preserves the superpotential. We want to point out that this quantum deformation algebra is not the usual UQ of SU2. Similarly, we can also consider the other broken generators and upgrade them to quantum generators. And we can prove that the theory is indeed invariant on the quantum enveloping algebra of PSU22/4 with a deformation parameter kappa. And this is due to a quantum group as PSU22/4 with deformation kappa. So let me summarize. We can generalize our manipulation of this A1 hat theory to all the angle 2 superconformal field theories obtained from the angle 4 super Yang-Mills theory by first doing an orbifold or orbifold projection, and then perform an exactly marginal deformation. The 4 angle 4 superconformal symmetry is always preserved for all these theories, albeit in a quantum deformed way. This symmetry enhancement from the manifest SU22/2 to the hidden quantum group PSU22/4 with a deformation is very useful, and it can help us organize the spectrum of angle 2 superconformal field theories. In addition, it's interesting to further explore whether there exists a Yangian-like symmetry of this quantum group. If we can prove this, then this will give a proof, or if we can show this, then we can give a proof of the integrability of angle 2 superconformal field theories. Okay, and this is in progress. Thank you.
Thank you very much. Let's thank Xinyu. Are there questions?
Oh, I could ask if I can be heard. So what does it mean in terms of representation of the multiplets? How do they look like in comparison to PS2/4? Are they the same dimension as before, or different, or what does the scale do to the multiplets?
It means that we first classify the angle 2 multiplets using the this group, this superconformal group, but actually some different multiplets can fit into a single PSU22/4 multiplets. and their, for example, their anomalous dimensions are related.
So are they also related that they like shifted by integers or say like half integers or?
No, it's more complicated because this quantum group also deform the Casimir, so it's more complicated.
And then does the symmetry go beyond one loop in a sense? It's a Lagrangian invariant?
All this discussion today is at the classical level. But we believe that this should be preserved even in the quantum level.
Could I ask a follow-up question to Kolya's? There are a whole bunch of protected operators in these n=2 theories.
Yeah.
There are many multiplets, I think.
Yeah.
This symmetry, how does it act on these protected multiplets? Do the protected multiplets, quote unquote, join up into bigger multiplets as well?
Yeah. Yes, they will definitely join up into this bigger multiplets, like the multiplets of this bigger group.
I mean, can you say anything more?
What we have done is for BPS spectrum, and we can see that for some states which naively their anomalous dimensions are different, can actually fit into a single multiplet. And this splitting is related to this kappa deformation.
Okay, thanks.
Any more questions? So if not, let's thank Xinyu for the very nice talk. And let's thank well, all the three speakers for the first session. And so now we move to the break / informal